Okay, super, awesome. Thank you for surviving till the end of the quarter. We are about 60 minutes away from the end of the last lecture for this course. So what I prepared for today is a set of interesting applications of the methods that we have talked about, and you will see how this can be applied to a wide range of domains. In particular, we will be looking at the applications of graph neural networks. And what I will try to cover in today is first about how can you use graph neural networks to build large-scale recommender systems. How can you apply graph neural networks to heterogeneous networks to predict side effects of different drugs that people take simultaneously, and then we'll also look something at the molecule generation. So essentially, that's the idea for today. So the first we'll talk about something called PinSage, which will be a graph neural network for recommender systems. And I should say that this is something that is running today in production at Pinterest and gives by far the best embeddings. I just saw that Uber published a blog post today that they are using this in Uber Eats to make some food recommendations. I was not able to finish the blog post. So this is actually used in industry quite regularly, and it's state-of-the-art method for recommender systems. So here is what we want to do and how we think about this, right? So what we would like to do is we have a set of users who is interacting with a set of items, and items could be like a user is watching a movie, a user buys some product, a user listens to music, things like that. And then what we would like to do is we'd like to personalize recommendations to the user, right? So that the user does not have to now go through a million songs and decides which ones they like, but based on their prior listening history, we'd like to recommend more songs to the user, right? And the basic intuition is the following. If you have a user X who comes to your website, and imagine you are selling music and they buy Metallica and Megadeth. I guess by names you should know what kind of bands these are, right? So if some other customer Y shows up and puts the Megadeth in the CD in the shopping cart, then probably our recommender system should learn to recommend Metallica to this user as well. Okay, so that's essentially the idea. And the way you can think of this is you can think of this to say, I have a set of users, and I have a set of items, a set of products. Users interact with items, and then based on these patterns of how users interact with items, I may be able to recommend new items to a given user. So the items they were not aware of. That's kind of the problem of recommender systems, or how we want to solve this. And in particular, the way we think of this is that the core operation in building a recommender system is to learn or figure out what items are related, right? So that, for example, based on the user's prior behavior, you identify a set of query items, and using this set of query items, you can then go and query your database of items, which could be products, websites, movies, posts, things like that, and then return a set of recommendations for that user, right? So the idea is user interacts with a set of items. Based on this interaction pattern of the user, I formulate the query, which is a subset of items that the user interacted it in the past. And then based on this query, I do kind of a search engine. I go to the search engine. Based on the query, I retrieve some new items, and I return those to the user. Okay? And those are my recommendations. That's essentially the idea. So the way you could think of this is if I have a user who has just interacted with this type of pin or with these types of posts, that it's about chocolate strawberry shake and things like that, right? So based on this information, I could go into my recommender system and say what other items are related. And maybe my recommender system would return this set of items, right? And you see that this is some fruit shake type thing, and here are some fruit shakes. Makes sense, right? But now imagine that the user interacted with a few more items, right? So something about healthy chocolate peanut butter chip muffins. I did not know healthy chocolate exists, but definitely something very healthy and something very delicious, cookies, right? So if the user has interacted now with these three items, my system should be able to formulate a query and based on these three items, retrieve new recommendations that now will be very different. Right now, the recommendations we are retrieving all have to do something with chocolate, and it's not really about fruit shakes anymore, right? So we should be able to learn that this wasn't really about shakes, this was really about chocolate, right? So this is essentially the problem we will be solving. Is given a query item or a set of query items, retrieve related items. And if I have this basic building block, then I can build a lot of user-facing products or surfaces based on this. So for example, in the case of Pinterest, if I have this kind of similarity function that tells me how related two items are, I can build this kind of endless feeds of content I recommend to the user. I can recommend related pieces of content, right? So if you look at one image, I can recommend related images. Or if you are looking at the image, I can now go and have a separate data set of ads, and I retrieve related ads, and I show them to the user, and things like that, right? So if I have this, I can use it in many different places. So now the question is, how do I define this notion of similarity between objects or between items? And generally, there are two ways how you can do this. One way how people do this traditionally is what is called content-based, right? So you would say, for every item, for every user, I have a set of features, and the similarity of two items is the similarity of the corresponding features, right? So if you have images of products, you would say two products are more similar if their product image is more similar. Or, if their textual description is more similar. And now, once you have one product, you have a set of features, and you find other products that have the most similar feature description. So this is called content-based. Another one that we will look at is called collaborative filtering or graph-based. And the idea here is the following. The idea is that users interact with items, and this forms some kind of bipartite graph structure. And the idea is that for a given user X, I want to find other users who interacted with similar items than the user X. And then, based on that, I make recommendations. Right? So the idea here is to say, I don't really care what these items are. I don't need to know anything about them. All I need to know is who are the people who like similar songs that I like. I have listened 100 songs. Each of you has listened 100 songs. So I could say, which of you has the most songs with me in common? And then, what are the recommendations I will get? If you and I have 80 songs in common, but you also listened 10 songs I haven't yet listened, those are the recommendations I would get. Because we look alike, right? You look like me, and that's why, and whatever new things you have experienced and you like, probably I will like as well. But what's the difference? The difference here is that we are kind of exploiting this idea that users are similar, and we don't really need to know anything about what these items are. They are just some kind of IDs, and we are saying, you have some song IDs, I have some song IDs, how many we have in common, which ones do you have that I don't have, let's recommend to me the ones you have that I haven't yet listened to, right? While up here, what we are really doing is to say, no, every song has a description, and now we find songs with similar descriptions that try to capture the audio and everything. And traditionally, this is if you have a lot of behavior data, if you have a lot of users, this works much better, right? Because it's kind of implicit, while here, coming up with these features and so on is super, super hard. So now that we kind of talked about this dichotomy, there are three things we need to do. First, we need to go and figure out how do we gather some signal of what is similar or what is related. That's always important, right? How do I know what are the songs you liked and what are the songs you didn't like? I need to get some data about that. Then, once I have this training data, then I need to build a method that will now go and for some unknown song say, how much will you like that song? So that's kind of the prediction problem, right? How do I extrapolate the similarity or the rating to this unknown set of songs that you haven't interacted with yet. And then the last question is, how do I evaluate? How do I evaluate the success of my method? Okay? And I will walk you through each of these three, how we do them, and we will start talking about how to use the machinery we learned in this class to solve these problems. And in particular, the case study we look at is the case study of Pinterest. Pinterest is the app where people take the images and they save images, or called pins, into collections. And the beauty of Pinterest is that you can have the same image that different users can save into different collections. For example, this particular person could take this image and save it into the vintage kitchens collection that they just created. And you know, maybe this person up here is really crazy about architecture, where there are these kind of blue accent details in the architectural style, right? So she created a board called Blue Accents, and she has 200 pins where there is some blue accent color in some architectural scene. And you know, my friend Ben here, maybe he created a board about fireplaces, and again, this image fits into this collection of fireplaces because this is a fireplace, right? And the idea is that essentially you have about 300 million users who are constantly taking images and saving them into collections. And you have about 4 billion images, about 2 billion collections, and over 200 billion of these edges or connections between images and the boards they belong to. Okay? That's the idea. So you can naturally interpret Pinterest as this bipartite graph of pins and collections they belong to. Every pin has an image associated with it and text, and every board is simply a collection of images or collection of pins. Okay? So now what we will do is the following. If we think about what kind of sources of signal do we want to use for our recommender system, as I said before, we have the feature information. Every pin has an image and a text, and we also have this graph information, right? About basically that puts pins into the same board. We have the boards here, we have the pins above, and then the edges denote membership. What is interesting is that the graph is dynamic. It is changing as people save more pins, and we need to be able to apply our model to this graph as it is evolving. The other thing that is important is that our goal will be to learn embeddings of items, to learn embeddings of pins. And the way we will then use these embeddings is to say, for a given pin, we will want to say, what are other pins that are most similar to this given pin, right? So the idea will be that if I have my pins and boards they belong to, I will learn an embedding for every pin, so that if you are, for example, looking at pin number 3, I will say, this is the embedding for the pin. This is now a point in some high dimensional space. Let me go and find the points that are closest to this point in the embedding space. And whichever of these other pins is closest, those will be my recommendations, right? So the idea is that I will come up with these embeddings of pins. Every pin is now a dot in some high dimensional space, so that if I am looking at this query pin, this is its embedding in the high dimensional embedding space. So now I will do the nearest neighbor search in here. This is close to the green thing, so I'll be like, this is related, this is what I will recommend, while these things are farther away, so they won't be retrieved, right? So our goal will be to learn how to take pins, how to embed them, so that similar pins are embedded close together. Yes?
In one space?
One at a time.
Okay.
I mean, how do you embed them? I will tell you how to embed them, of course. But you kind of embed one at a time, right? Like you will have some function that will take an image and give you some 300 dimensional vector for it. So this will be like a 300 dimensional space. And you will, right? And then you'll take the second one and embed it, and everything will be in here. Then the question will be, what kind of you didn't ask me is, how do you quickly find nearest neighbors in this high dimensional space? Because if you have now 300 dimensional space with about 3 billion points here, you cannot go and compute the distance between the query and every pin and find the closest ones. You cannot do that. So if you want to know how to do this super fast, you should take my class next quarter. It's a method called locality-sensitive hashing that allows you to do this in constant time. And that's what powers everything, right? You need this kind of nearest neighbor search in high dimensions whenever you are doing anything with embeddings, and without that, embeddings are useless. So you really need that, okay? So this is what we will try to do. And our goal, of course, will be to learn this function that takes the objects and puts it into 300-dimensional space so that related objects are close together, okay? So here's the idea. At very high level, our goal will be to embed related objects together using some user behavior data. We will come up with these types of triples where we'll say, here's the query pin, here is a related pin, and here is an unrelated pin. And our goal will be to say, let's now identify the embedding, here I call it Z, such that the distance between cake 1 and cake 2, so the query cake and the target cake, is smaller than the query cake and the sweater. Okay? And if I'm able to do this, now I'm able to give you a good recommendation, right? If you are looking for a cake, the other cake will be closer than the sweater. So for the cake, I won't be recommending you a sweater, but I'll be recommending you a related cake. And that sounds like a good recommendation. So how are we going to do that? We are going to take this bipartite graph of pins and the boards they belong to, and we will think of this as a graph neural network, right? So we will say, let's create an embedding for every node in this graph, but rather than just use the image and text information about each individual pin, let's unroll this network into a graph neural network, okay? So now every circle here is a pin in this graph, so that then basically what we are doing is to say, let's create an embedding for cake number 1, let's create an embedding for cake number 2, so that the distance, let's say, will be small. And if this would be an embedding for the sweater, then I'd say the distance has to be large. Okay? That's the intuition. So rather than just computing the embedding directly from the node itself, we will also embed it based on the structure of this network, so that the nearby in the graph nearby pins will also provide the information to the embedding of the pin. So that's essentially what will be happening, right? So the idea will be, the idea will be the following, right? The idea will be that for every target pin, I will unroll the bipartite graph to get the graph neural network. So this means that now pins will have embeddings at every layer. At the bottom layer, I will simply initialize the embeddings based on the textual and visual features of every pin. And then I will learn how to now aggregate this information, combine it with the last target pin to come up with the final embedding for a given pin. And the point is that this will be better than just embedding the pin directly, because I'll be able to reuse the information from the neighbors in the network to come up with a better representation of a given pin. That's essentially the idea, right? So if I want to create the embedding for that little cake, I will also look at what other cakes are pinned to the same boards as my cake, and I will use their features and learn how to propagate and aggregate them to come up with the embedding of the cake, right? So what's the idea when we talked about graph neural networks? The idea is, rather than creating an embedding for myself, for the cake, I will also look at what are other cakes nearby and use their features to enrich the feature description for the target cake, right? So that's essentially the idea. So why will this work? This will work because we are generating an embedding for every pin, right? Based on both the feature information and the graph structure. And using the graph structure, we are able to borrow information from nearby nodes. And why is this important? This is important because if you would only consider the image itself, you'd be able, sometimes computer vision will make silly mistakes. It will confuse the garden fence for this type of bed railing. It will confuse a carpet on the floor for some tapestry on the wall. It will confuse ground meat and soil, or brown rice and soil. It's very easy to confuse. They all kind of look grainy and brown, but one is to eat and the other one is soil, right? So you will make this kind of silly mistakes. But if you look at the graph information will tell you that garden fences are in one part of the graph and beds are in the other part of the graph. So this will allow you to resolve your embedding much better because you'll be able to borrow information from nearby nodes, right? And if you are able now to borrow this information effectively, these pin embeddings will then become essential to create many different, as I said, products. Like you can do related pins, you can create these endless recommendations, you can use this to cluster users based on interests and things like that, right? But the key insight is that rather than creating the embedding for the pin based on its image representation only, you also take the pins that are nearby in the graph and use pieces of that information to enrich the embedding for the target pin. That's essentially the idea. And because pins that are related will be close in the graph, you'll be able to distinguish things that may look visually very similar, right? That's the idea. So how are we now going to do this? So the first thing is, where does the training data come from? So the training data is, we need to identify pairs of pins that are related. And because you have 300 million users interacting with these pins all the time, you want to say, for example, the heuristic how we'll say two pins are related. We will say two pins are related if they've been consecutively saved to the same board in very short time interval, right? So the idea is you are looking for, I don't know, what are you looking for? I don't know, cute dog pictures, right? And you just created a cute dog's board, and now you are adding pins to it. And if you add two pins to the board in a very short time, then we say they are related, right? So these two pins are related. You know, somebody is creating something about Navy and sailors and created the sailors board and saved this together. And this is some, you know, cartoon character that again are related, right? So those will be now your positive training examples by basically looking at what people save into the same board in short time interval. And then what will be negative examples will be just random sets of pins, right? I'll just take a random pin and say that's a negative example, okay? So now I have training data and I can get billions of these things, right? Now that I have obtained training data, then I will train a graph neural network to generate embeddings for pins such that the positive pins that are related are closer together than pins that are not related. Now that I have trained my model, I will apply my models to generate embeddings of all the pins, as you asked, right? And now, at the time of recommendations, when I see user is looking at some pin, I will do the nearest neighbor search based on these embeddings and return related pins. Okay? Make sense? Yes? Yes? Okay. So, what is my objective function? Right? My objective function is the following. Again, as I said, what I want is pins that are close together, that are related, have to be close together. Pins that are not related have to be far apart. The way I think of this, I say, let's go over all my training data, and this is are the coordinates of the pin. The dot product, is essentially a cosine similarity. So you can think of this as similarity. And what do I want? I want to have my loss to be small. So I want this product to be large, and I want this product to be small. Right? If this is large, then I have a negative here. This will be little, and my loss will be small. And and here I want the other way around, right? This is a positive pin and a negative pin, right? So this is cake 1, cake 2, cake sweater. I want this dot product to be small. I want the similarity between the embeddings of cake and sweater to be small, and I want similarity between cake 1 and cake 2 to be large, right? And this is called the max margin loss. The reason why it's called the max margin is because I have this delta term here, and this tells me how much more similar is the positive pair versus the negative pair, right? And I want to select the embedding Z in such a way that this loss is minimized. That's what I want to do. Okay, so now how do I do this? So there are 4 key components to be able to do this at the large scale. So the first thing is that for every pin, we are going to generate the computation graph, right? As we talked in the lecture about graph neural networks. And then as we are doing the forward pass to come up with the embedding for the pin, we will have these operators, these aggregators and transformations that we talked about, right? And we talked that these aggregators and transformations are learned, right? There will be some way to aggregate features from the neighbors and transform them, and these two guys will be learned. The way this will work is that now we will be able to generate a lot of these small computation graphs and send them to the GPU for processing, okay? And at every iteration, at every computation graph, we'll be able then to compute the embedding for a single node, okay? That's the first thing, is that we will never work with the entire graph at once, but we will create a lot of small computation graphs, one for every node, and then we'll just work with a lot of small computation graphs. And this is very useful and very elegant, because this means I never need to work with the entire big graph. All I have to do is work with a lot of small graphs, right? Which helps me a lot. So that's the first thing. The second thing that becomes very important is when we do aggregation. When I initially talked to you, we said, oh, just take all the neighbors and aggregate. But the point is, you don't want to do that, right? If you have a super popular pin, I don't know, you have a Lady Gaga or I don't know, Kim Kardashian pin, right? You don't want to aggregate from, I don't know, all the followers of Lady Gaga. The reason I use Lady Gaga is because she used to be the most followed person on Twitter, and entire Twitter infrastructure broke whenever Lady Gaga tweeted. Because basically when she tweeted, they had to take her tweet and put it into the queue of every single user that followed her. And that broke Twitter. So that's why I use Lady Gaga. So the point is, if you have a high degree node, then you are aggregating from super many other pins that share the board with that pin. And you don't want to be doing that. Right? So I don't know, what's an equivalent of Lady Gaga on Pinterest. Maybe it's, I don't know, some chicken recipe or whatever, right? So, but the point is, we don't want to do that. So what do we want to do? We want to somehow intelligently select what neighbors are we going to aggregate from, so that we don't aggregate from all the neighbors in the graph. And the way we will do this is that we will use PageRank to identify what are the most important neighbors to aggregate. And when we aggregate, we won't aggregate by just averaging or summing up the signal from the neighbors, but we will use these PageRank scores to do this in a weighted manner. And this is called importance pooling. Pooling means you collect the information, you add it up, but you add it up based on the importance of every node. You don't do it just kind of uniformly. That's essentially the idea. So how are we going to do that? If I have my pin I'd like to embed, then, for example, this pin has a lot of other pins with which it shares boards. So what I will do is I will use PageRank random walks to determine what pins are most related to my query pin based on these visit counts or random walk similarities. And the idea will be that then I will just pick a couple of the most important pins and aggregate information from them. So let me try to explain how this will work. Right? So the idea will be that rather than aggregating from a huge number of pins, I'll only aggregate from a small number of pins, let's say top k. And the way I will select the top k is by starting a random walk from my query pin, then get a visit count for every other pin, and I will take top k other pins based on the visit count. Okay, so let me try to explain. Right, so the idea is I will start a random walk here in my graph. Every other pin will get a certain visit count, and now these numbers correspond to those visit counts, and I will take the top, let's say 5 pins with the highest visit count. Okay, so here are now the top 5 pins with the highest visit count. I will now normalize their visit counts, and I will use this as the importance weights, right? So when this guy will collect information from its most important neighbors, this is the weights by which this weighted summation will happen, okay? That's essentially the idea. So in the graph sage, when we talked about convolutional graph neural networks, we used min pooling, where the idea was you just you just sum up the information from your neighbors. In PinSage, we will only sum the information from the top k highest PageRank score neighbors, and when we sum it up, we will also weight according to these visit counts. And as I will show you later, this really makes a huge difference in performance. And in practice, we use k equals 50. So we take at most 50 neighbors of a given pin, rather than taking all of them. Okay, so that's number 2 that is important. And then the last thing that is important is that if you think about these computation graphs, when you are doing a forward pass, when you are computing embeddings, you will notice that there is a lot of redundancy, right? What do I mean by this is, for example, these types of computations, they are all redundant, right? Like I make this computation here, I make the same computation here, I make the same computation here. Then it's even worse because, for example, this computation also happens here, right? So whenever I'm computing embedding for this guy, this subpart here also happens here. And it's the same messages. So I'm kind of doing this twice that I shouldn't need to be doing. I'm computing this thing here, I'm computing it here as well, and so on and so forth, right? So there is a lot of redundancy that happens in computation if you are not careful. The way you can avoid this redundancy is to try to compute this entire structure only once, save it, so that when I'm creating embedding for this guy, I don't even need to recompute this, but I can just say, oh, I've seen it before, let me just reuse it. And there is this computational framework called MapReduce that allows you to do this super effectively over thousands of machines super easily. And again, I did not tell you what MapReduce is, but if you are intrigued, you can take my class next quarter. Okay, so the second advertisement for my class. Let's see how many am I able to sneak in. Okay, so this is another thing that becomes important in practice. And then the second thing that becomes very important in practice is the following: is this notion that what do we want to do, right? Like we say we will learn embeddings, and we wanna when we come up with the query, we want the positive example to be closer to the query than the negative example, right? That was our objective function. But when we retrieve in the deployment, all we care about is what are the top 100 closest objects, right? So in some sense, right, I have a query point, and then I measure the distance to every other pin to every other point. But I will never care whether the point at rank 1 million is more relevant than the point at rank 1,000,010. All I care about is the top 100. And then for the rest, I couldn't care less, right? I don't care whether something that should be at rank 2 billion is now at rank 1 million. It's like infinitely far for me, I don't care. But what I really care about is the top 100, because I can take the top 100 and show them to the user, right? And now if you say that, so what am I trying to say? I'm trying to say that when we learn these distances, these embeddings, we want to learn with like super fine precision, right? Because we really care about what are the closest objects. And now if I give you these types of easy negative examples when I'm saying, oh, if you want to compare tapestries, here is some random hat and it's unrelated, you'll be like, yes, of course, obvious. I knew this already, right? But the point is that we really want to compare, what tapestries are more related and what are less related. So the idea is that if we want to learn with this kind of super fine precision, this is just too easy, and it will take forever for us to learn what is truly related. So the idea is to come up with this notion of hard negative examples, right? So that early on, we are able to use negative examples that are easy, but as the training progresses, we will be using harder and harder negative examples. And this will force our model to learn better and better and better. And as I said, why do we care about this? Because we only care what are the top 100 closest pins out of the 3 billion, and the rest we don't care about. So the idea will be, right, if this is my query, and I know this is a positive example, then if I pick some random pin, it will be something unrelated. And it is very hard to learn that this is more related than that if all I have to give you is things that are related and something that's completely random, right? But if I have this notion of a hard negative example, and I tell you not only that these two are more related than those two, but that these two are more related than those two, then you can really learn, right? So basically what I'm trying to say is intuitively, if you think about how do I sort numbers, right? In some sense, we want to learn how to sort numbers. And if I just give you random pairs of numbers and say these two are closer than those two, it will take you forever to truly sort the numbers. But if I give you pairs that are very close and I say this one is bigger than that one, then you will sort much faster. And this is what kind of quicksort is doing, right? And it's a similar idea here. How do you obtain hard negative examples? It's a heuristic. The way we use the heuristic is to do the random walk, basically to do the random walk on the pin board graph and take a pin that is at a rank, let's say between 1,000 and 5,000 and say this is a hard negative example, right? So this is something that is still related, but it's not really super related, right? So here, it's the same thing, but these are flowers and this is a bird, right? So that's why it's not related, right? So, and how are we now training? We have this notion of curriculum training, where there is a particular curriculum by which we train the system, where at the beginning we train the system to say these two have to be closer than those two. And as the system learns to distinguish these easy examples, we start to throw in these harder examples, where we say the first two have to be closer than the query and the hard example. And this way, the system learns much, much better. Yes?
So if we're basically using random walks as a way to label our positive versus negative examples, then have we seen as a baseline how much random walks will do, like how well they'll do on recommendation? And I understand they probably don't have the same computational benefits, but...
Great. So I will show you the following. So here are my results. Okay, so no, perfect timing, right? So how are we evaluating this? We say you are looking at pin Q, and I want to predict what pin are you going to save next, okay? And that's the pin X. And now I'm asking, if I now measure the distance between Q and every other pin, how highly ranked is X? Okay, that's my question. And I have two metrics that tell me how well you are doing. One is called mean reciprocal rank, where I would take the rank of X divided by the total number of pins, and then take a reciprocal of that and compute the mean. And the higher the number, the better. This is called mean reciprocal rank. And then this other metric, it's called hit rate. And this means the point of this metric is how often was this pin X among top K? Let's say top 100, top 500, right? So I'm just saying how often were you able to put this related pin X among the closest 100 pins, okay? So now let me tell you what the baselines are. The first one is if I use state-of-the-art computer vision to learn embedding for every image, and I'm now comparing distances between image embeddings, and that gives me, let's say, hit rate of 17%. If I use text data only, it gives me 14%. So it works worse than the image only. If I combine text and image into a longer vector that, the first half is visual and the other one is textual, it works quite well. It almost adds the performance together, right? It's 27. Now, here are the graph-based techniques. If I'm just summing information from all the neighbors, or aggregating information from all the neighbors, but here I'm using the max, here I'm using the mean, I do between 39 to 41. So I do 50% better than what vision can do. If I'm using hard negative examples, that further improves. And if I'm using this notion of hard negative examples and I carefully select using this PageRank idea what neighbors I aggregate from, then I get another almost like 50%, right? And now this is the difference, right? It's like visual gives me 17 and this gives me 67, right? That answered kind of your question?
Yeah, although I think the baseline that I was thinking was just like random walks alone. Like if the latest thing that you added was...
I should have that actually. I had it on some other graph.
Oh.
We tried that as well. The point with random walks is that it is somewhere in this range.
Okay.
It's not that good. But the point with random walks is actually random walks are amazingly cheap. So doing this random walk in real time, simulating it, is about 10 to 100 times cheaper than doing nearest neighbor query in 300 dimensions. So that's amazingly computationally cheap. Yeah. And if you are paying for Amazon Compute, which you have to, right, like or Pinterest does, then the cost becomes a huge or an important consideration. So when you are deploying the systems, you are always like, how much does this cost? How much benefit does it give me? Yes, Daniel.
Also, random walks by themselves wouldn't be inductive, right? So if we have a new node that doesn't have any edges, we can't do random.
Correct. Then what you are now saying, it's another good point, is that when you build recommender systems, you have this issue of what people call cold start, which is you get all these new things that you have no user engagement with, and you don't know how to recommend those. And you kind of have this problem that you have all this old content, that you have a lot of user engagement, so you know how to recommend it, but you have all this new content that you have no information about. And you need to balance between how much do you try to push this new content to gather information about versus how much are you exploiting the old content. But you don't want to just exploit the old content because then you will become too stale, right? And that's a very kind of interesting question. So let me give you a few examples. So here's my example of some plants growing. If you do the visual comparison, it's basically bibimbap, brown rice, things like that, right? So I was not making that up. If you are doing it based on text, you kind of get the idea that this is gardening and that's also gardening, but it kind of misses the point. The graph-based system gives you something, but like visually, again, doesn't really match. If you would use the pin sage, here are the recommendations you would get, and you see this is, gardening small plants. These are also some small plants and things like that. Here's another example. Some settlers cutting down a big tree. Visual gives you, black and white images that are visually similar, but totally misses the content. This is some war and some old farmers, nothing to do with logging. If you use textual, you get kind of logging and forests, but it doesn't have enough kind of resolution. Graph-based kind of gets things right, but again, it doesn't give you the good recommendations. And here, we actually get the right recommendations, right? Some historic photos of people cutting down trees. Yes?
The question was, so things, say 2 nodes they all share the boards and they're
Yeah.
all very highly visited. Will there be kind of like a loop thing? Because they have high correlation with each other. They tend to appear all the time in terms of coordinates to other.
Exactly. They would co-appear, and that's good.
That's what we want.
That's in some sense what we want, right? Like, because what this will allow me to do, even though I may look like a war picture, I co-appear with many other wood pictures, so I know I'm a wood picture. That's essentially what this will allow us to do. Like, even though I may think, if I'm this picture, I may think, you know, these are rifles, but no, these are not. These are, I don't know, chainsaws or whatever, right? So that's the idea.
About the loop, kind of the loopy belief permutation problem in this case is we do want highly relevant information.
But we don't worry because we only unroll this for about 2 steps. So it's not this kind of loopy belief propagation where you run this until it converges. You only unroll for a limited number of steps. Yes? How do we ensure diversity? We don't ensure diversity, right? So the goal here is not to have diversity. The goal is to really learn what is super similar. And the way it turns out, to ensure diversity in recommender systems, yes, it's very important, but you don't ensure diversity by having random recommendations. The way you ensure diversity is to say, let me retrieve whatever I think is the most similar, and then I will randomize at the end. So you kind of build diversity on top of something, not as a part of the core. Because if you do it, then just everything, like, it's super hard to work with. So if you need the diversity, you can diversify this by going farther by the distance, by having some way to diversify, right? But you would do this on top. Yes.
To be clear, just with the results on the last page, the mean reciprocal rank of 0.5 means that it was in the next 2 images was the next image pin. Right?
That would be the case. But I don't think we were at 0.5. We were at 0.3, right?
It probably went to 0.59, right?
Perhaps. Oh yes, you're right. So this means we are getting things very, very high. Yeah, it's a good question in what units this is. So there might be some magic constant here. Right. So it's a good point. Yeah, this would be very high, right? So like if you have mean reciprocal rank of 0.5, it would mean that on average you are kind of at position 2. But of course, another thing to remember, because you're doing mean reciprocal rank, is that lower ranks are far discounted, right? So that's important to know, right? Just give you a couple of more examples. This is the query. This is what what visual-based recommender system would give you. This is what the pin sage would give you. And again, you see this is some kind of porcelain doll. You get a lot of porcelain dolls. Here it's similar, but then these porcelain lights come in that shouldn't really be here. I have another cool example because nothing is perfect without cats, right? So if this is your query, you know, cats with these funny hats, this is basically sorted by distance, and you see it's relevant, right? Like you see cats with all kinds of good hats. Here, maybe, you know, some are okay, but you see it kind of deteriorates very, very quickly with quotes, with cute pictures of dogs, things like that, right? While here it's kind of spot on. Yes?
Have you tried to jointly learn the feature extractors for the images with the recommendation system?
We did not. It would be interesting to do, but it would be like the scale is scary. Right, so that's why I think like it would be quite hard to make this work. But yeah, it's definitely a clear good idea.
Yeah, this might be a scale issue too, but do you think there's any limitation in like expressivity at all? The fact that there is only one embedding per pin. So for example, like in the beginning you gave that example of the thing that could either be related to like blue accents or could be related to like kitchens or whatever.
Correct.
And it makes me think of, for example, in natural language processing that we've seen that like contextual word embeddings have made a big difference in the sense that like words also have contextual meaning.
That's a great point. So there is actually follow-up work where you try to learn multiple of these embeddings or try to learn embeddings that are contextual and things like that. That's definitely a very very clear, good direction, and it helps a lot. Okay, good. So this was topic number 1. Let me do topic number 2 as well, because it will be interesting. So this will be now, again, graph neural networks, but to a very different domain, and it will be to heterogeneous graphs. So the motivation for this from technical point of view is, so far we only applied graph neural networks to simple graphs, graphs where basically we had a single type of node and a single type of edge. But if I have multiple types of nodes and multiple types of edges, how would I apply graph neural networks? This is what we are going to see here. What the application will be, it will have nothing with graphs. It will see. Okay, so here's the problem. The problem is, for every drug, we know what side effects it causes. What's the problem? The problem is that many people take multiple drugs at once. And if you take multiple drugs, it's not the case that you would have a union of side effects, right? You may have a drug that gives no side effects, another drug that gives no side effects, but if you take the 2 drugs together, you get headache, you get runny nose, it's super bad, right? And this is called polypharmacy, that you have kind of multiple drugs, right? It's the use of multiple drugs for a disease. So the statistics is that about half of the people over 70 are on 5 or more drugs at the same time, right? And at least my grandmother, right? She has this little set of drawers and little boxes, and my mother would fill that up for her, and then every day there's the different little box that she opens, and she takes whatever pills are in there, and there is an amazing amount of different colored pills she takes, right? So that's kind of what things are. And of course, the problem is that when you do drug trials this way. You take people, you put them on one drug, and you see what happens. And there is just too many drugs that you would now do a drug trial and say, let's try a pair. Let's take a triple and see what happens. So the only way today we learn about these side effects is that essentially doctors keep prescribing whatever doctors prescribe. If the patient comes and complains, then, and if the doctor takes enough attention, the doctor would report this to FDA. If enough doctors would report, FDA would add a line into some Excel spreadsheet by saying, if you take this, this is going to happen this often. That's how we learn. So we kind of learn a trend. So the point is that these side effects affect about 15% of US population. There is some huge cost assigned to this, because essentially a side effect means that you basically got a new disease, or you have another kind of side effect disease that you have to now treat, and you will get another drug and things like that. Identifying, as I said, identifying the side effects manually is super complex, or it's super inefficient, because they are rare, they may only occur on a subset of patients, they are not observed during clinical testing, so the only way we learn about them is through this reporting system that's very inefficient. So the question is, could you use computational methods to predict what side effects may happen? Okay, that's the question. So, and the idea will be, right, what if I use some molecular data, some pharmacological data, and be able and try to predict what kind of side effects a pair of drugs will treat, right? And if I would have this system, I could use it in many different ways, right? A doctor could use it to say, this patient is on this set of drugs. If I add this other drug, what might happen, right? So the idea is that for the purpose of this lecture, we will ask the following question: if a patient takes drugs C and D, what kind of side effects might we expect? Okay, so given a pair of drugs, we want to predict what kind of side effects these drugs may lead to. That's the prediction problem. And now we will formulate this prediction problem. We will create this heterogeneous network that will be the following. We will have 2 types of nodes. We will have the drug nodes, and we will have the protein nodes. Okay? Proteins are molecules in our bodies that physically come together to do various kinds of biological tasks and processes. And how drugs work is that drugs target or change the behavior of proteins so that these proteins can do their job or cannot do their job, right? So biologists spend a lot of time physically testing whether two proteins come together in a body to do a given function. And this is called a protein interaction network. So we have about 20,000 proteins or 20,000 protein coding genes in our bodies. So we'll have 20,000 nodes. Biologists experimentally validate each of these edges, these interactions between proteins, and that will be the bottom layer of our network. Every protein will also have some feature vector associated with it, telling us about the structure of the proteins, its role, and so on. Then, whenever you want to get your drug clinically approved, you need to know how it works. So you need to say which proteins does this drug bind to, or which proteins does this drug interact with. So you also get these edges here, in some sense, for free. So now, what are the edges between the drugs? The edges between the drugs are the side effects, right? So this would say if you take drugs C and M, then side effect number 1 will appear. While, for example, if you take C and D, side effect number 2 will appear. And of course, again, every drug will have a feature vector associated with it that will tell us about properties of that drug. Yes?
The reason why some drugs have no interactions with proteins is just due to chart abstraction?
Correct.
Okay.
But you generally wouldn't, at least today, if you want to have a drug approved, you need to know how it works. So you need to figure out those edges. But traditionally, there might be drugs that don't have these edges because they are kind of old and they work and we don't know how or why. Okay? So that's the idea. So now what is the network prediction task? The prediction task is, given a pair of drug, how likely is an edge between them to exist? And edge also needs to have a type because there are different types of side effects. So we will have 1,000 different side effect types. So we will be basically doing a link prediction where we can predict a multiple of 1,000 different edge types, right? Because multiple side effects can occur. Okay, that's the prediction task. So the idea will be we want to predict labeled edges between drug nodes, right? So basically the idea is what is the likelihood of this type of edge to occur, right? What's the probability that an edge between C and S will occur, and this edge is of type 2 because this is the side effect type 2. Okay, that's essentially what we will be trying to predict. And again, we will be using graph neural network to be able to do this. So how are we going to do this? We will use graph neural networks to compute messages over different edge types and then learn how to aggregate them, right? So if I have my heterogeneous network, here is one layer of the graph neural network to compute the embedding for this node C here, right? And the architecture is the following. I will take information from the proteins, aggregate it, transform, and pass it. And then for every different edge type, this is side effect type number 2, side effect type number 1, I will have a separate aggregation architecture, right? So here, for example, if I look at side effect R2, and I'm looking at the node C, I'm aggregating from D and S, and then for side effect R1, which is some gastrointestinal bleeding, right? So basically bleeding in your gut, I will be aggregating this over nodes that are related to C via relation R1, so I'll only aggregate from M. So this is the path, right? And as I said, we will have 1,000 different side effect types. So we will have 1,000 of these types of things and then one here. And this will now come together to create a embedding for a given node. And of course, we will unroll this for 2 or 3 steps, not just one step.
In the case where two drugs come together to create multiple side effects, do you model that as multiple edges or as a new edge type entirely?
Multiple edges. So let me explain. So this is now to create an embedding for one drug. And as I said, this is just one level. We will do this for multiple levels. Now we need to predict drug types. the edge types. The way we do predict the edge types is to say, here's the embedding for one drug, here's the embedding for the other drug, and now I want to create 1,000 different predictions, one for every edge type, one for every side effect type, right? That's the way we will do this. So if you think about this, how will the network architecture look like? It will look like this, right? I have a neural network to create embedding for one drug. I have the neural network to create the embedding for the other drug. I get the embeddings. These are kind of the encoders. And now I have a decoder that makes the predictions. Okay? And now, based on my training data, I can now do back propagation this way, right? That's essentially the idea. So I won't go more into details, and I will leave it at this kind of high level, and I did not explain how exactly you do this decoder here that gives you 1,000 different predictions based on these embeddings you learned. How are we going to do this? So we will have a protein-protein interaction network and a drug-target relationships. And then we'll also have the side effects between different drugs. We will construct a heterogeneous graph out of this data. We will train the model to predict known associations between drugs or known side effects between drugs. And at the test time, given a pair of drugs, we wanna predict what side effects they may cause. And we will, use some set of known side effects to train and some other set of known side effects to test. So now the question is, how well are we able to do this? These are the 2 layers. So when you go 2 hops away in the graph neural network, if you do the 3-hop graph neural network, these are the precision. This is the area under the precision recall curve. This is average precision at top 50. This is the AUC, the AUC or the area under the ROC curve. Higher is better. Node to VEC we talked about, so you guys know what this is. If you just use drug features, this is how well you can do. If you are using the state-of-the-art method to do these things, here's the performance. And you see we are doing quite well. What is maybe more interesting is that you can use this model and ask it to make novel predictions. So what we did is we take all drug pairs, and for every drug pair we said, what are the predictions the model makes? And here are the top 10 most confident predictions that the model makes over the data. These are predictions. This is not cross-validation. These are just pure predictions of the model. So the model says, if you take this drug and that drug, you will get cluster headache. And if you take, I don't know, these 2 drugs, you will get something I cannot even read, right? So you'll get some other side effect, right? Or if you take these 2, you'll get, this type of inflammation, right? So these are completely novel predictions that nobody knows whether they are true because they are not part of the data set. So what we did here is actually we went to clinical notes and said, has there any research been published that could indicate that these predictions are true? And if we did this, we were able to verify 5 out of these 10. So I think our data was collected in 2016. So you see, for example, some of these publications actually come after our data was collected. So these are brand new predictions that were never in the data. But it turns that half of them we were able to find evidence for. Of course, the other half are not necessarily mistakes. They could be just unverified hypotheses, right? So this is quite impressive, right? That basically we are able to make predictions that half of them has been kind of independently verified, and we could never have guessed this using our data alone. Yes.
What's the ethics behind verifying these interactions? And is there any concern that publishing a list like this, for example, might cause doctors to, as a precautionary measure, not prescribe them together? Then you'll never know. I mean, for some of these things, you can test them in lab cultures and things like that, right? So you don't necessarily
need to, I mean, sure, if the side effect is headache, a cell wouldn't have a headache. But for certain other things, you could try to test them in the lab. Another thing I think that's interesting here is that this is all population level. So there is no individual information that comes into this prediction. What you would really like to do is also somehow account who the individual was. But right now, FDA is not collecting any of the data. They just say this tends to happen or whatever. So there is a lot you could expand this work in many different directions. So that's a very good question. Okay, good. Anything else? So if not, let me maybe just quickly say one more thing. I'll try to do very quickly. Just give you an overview of what the problem is. So the problem is, we talked about graph generation using graph RNN. The question is, can you do graph generation in a targeted way? So what do I mean by this? I'll skip this and say, can I generate graphs that are optimal? That's the question. And one place where you would like to generate optimal graphs is when you do drug discovery, right? Where you would like to say, I want to generate molecules that are valid, that are realistic, right? Valid means they obey the rules of chemistry. Realistic means they look like real molecules and they optimize some property. For example, they are not toxic, right? So I would like to generate graphs that are chemically valid, that look like real molecules, and that optimize a certain chemical property, right? And it turns out that you can do this. It turns out you can train graph generation such that it also optimizes a given objective function, like toxicity or drug likeness and things like that. And that's very interesting because now we are saying, can I generate structures that optimize a certain objective function? And you guys are welcome to read this paper that is the extension of what we learned in the class that tell you how to do this. And why is this cool? Because what you can do, for example, you can do this type of editing where you can start with a structure, and because we are generating the graph step by step, I can take some structure and say, I want to take this structure and I want to kind of print out the rest of it such that some objective function will increase. So this structure has the value of this objective function 0.8. After my system takes this, prints out the rest of the molecule, this objective function increases, right? Or, here's another example, and now I printed the rest of it, and now the objective function increased, right? So basically the idea is you can generate new molecules, or you can take partially built molecules and generate the rest of it so that you optimize a given function. Like here is something that chemists call log-P, and this is, I think, the higher this value, the more drug-like the molecule is, and chemists care about this. Okay, so I know this was fast, but I just want to kind of get this idea out and get you thinking about how you can basically take a graph, take a partially built molecule, and build the rest of it to optimize some objective function. So that's what I wanted to do. So I just want to quickly, in the last 5 minutes, kind of conclude the course and say a few thank yous. So what is next? What is next is just a reminder that we have the project write-ups due on Tuesday next week at midnight Pacific time. One of the team members uploads the PDF to Gradescope. And don't forget to tag your other team members, right? Tag your team members, okay? And then we'll have a poster session next week on Thursday between the final exam time. This means between 2:15 and 3:15. It will be outside the classroom. So basically here in the foyer of Huang building, just like outside the classroom. All groups with at least one non-CPD SCPD student should present, and there should be one person at the poster for the entire duration of the 3-hour thing. Meaning you can swap members, but there should be somebody ready to to answer questions at your poster at all times, and other members can go around and talk to other people. How does this look like? Basically, the TAs will go and visit each poster, be ready to give a 2-minute overview of what you did, right? To present your poster, present your work, and basically give some kind of elevator pitch or a quick summary of what you did. We will post more instructions on Piazza on how the poster session will be. The second thing I should say is, what are some next courses that kind of build on what we learned? So in the winter, I'll be teaching this course called CS246, Mining Massive Data Sets, which will be all about data mining and machine learning over large data sets and building scalable algorithms and building algorithms where the data doesn't fit into the memory of a single machine. This is super useful, especially for people who are thinking of getting a job in industry at some point in time. It's probably the most useful class, because in industry, data is always big and you don't know what to do. Then the second thing that we teach, which is in spring, it's a project-based class called CS341, and essentially the way we think of it is either projects from 224W or the theoretical knowledge from 246 gets applied in a quarter-long class, where, similar to this class, we provide compute infrastructure, we provide mentorship, and people are able to work on their projects, and at the end, hopefully publish them. And we get quite a few publications out of either the 246 or from 224W through this 341 class. What are good places to publish these types of research? There are data mining conferences like KDD, machine learning conferences like ICML, NeurIPS, iClear, and then kind of web, online, social media conferences like World Wide Web or Wisdom, WSDM. And then there are also dedicated journals that care about network science or algorithms for networks, like Journal of Network Science or Journal of Complex Networks. So that's kind of a good overview. And then, what are some other relevant courses? If you want more on the machine learning side, general machine learning or the deep learning. If you want more on the network side, in terms of social science, there are very good courses in MS&E. If you want more about big data, you can take 276, which is information retrieval web search, or kind of advanced database data management courses. So this is what I wanted to tell you, kind of what the next steps for you are in your path through the Stanford system. So to finish the course, I wanted basically to say thank you twice. First, I wanted to thank the TAs and Michele for, I think, doing a fabulous job and amazing job and making everyone's experience with this class great and smooth and seamless and so on. So thank you for the TA team. I think they really deserve a thank you. Yes. Thank you. And then I should also say thank you all for attending the course, spending a lot of time and energy doing the homeworks, coming to lectures, watching videos, and also working on your projects. I think you learned a lot. You probably learned more than what you think. Thank you also for doing a great job on the projects. And really thank you for the hard work. And I will see you at the poster session. Thank you, guys.